We learned in the last lecture about dynamic range. We're going to learn a little bit more about it in this lecture as it's a very useful tool for sonographers. Dynamic range is a method of reporting the extent to which a signal can vary and still be accurately measured. When we talk about dynamic range, we talk about the sensitivity that each ultrasound component has. You'll learn in a moment that the transducers are actually the most sensitive. They have the widest dynamic range because they can detect the most signals that are coming back. They can detect really weak signals and they can detect very strong signals and tell the difference between all of them. As we move through ultrasound components getting down to the display, the dynamic range changes. It becomes less sensitive to those echoes. So we compensate for that with compression. Compression is the process of reducing the dynamic range without introducing any errors. This is an operator adjustable control of dynamic range. And it's going to assign weak amplitudes to the value of 0, and it may assign strong amplitudes to the value, the strongest value, but all the reassigned echoes are still in the appropriate order. So our ultrasound units can only process signals accurately within a particular range. The dynamic range describes the extent to which a signal can vary but still remains accurate. Dynamic range is considered a ratio of two numbers, the ratio of the largest to the smallest signal strength that each component can process. We measure dynamic range in decibels, and we consider the dynamic range of the display to indicate the number of gray shades that are displayed. So here's 3 examples from a phantom that is being used on the ultrasound machine. Picture A has the dynamic range set at 50 decibels. You can see it looks pretty grainy. We're getting a little bit more into a black and white type image. This is considered low dynamic range with high contrast. Image B then is set at 70 decibels. We're starting to kind of smooth everything out. We're getting more options of grays. We're getting mid-range grays being displayed, but we still see blacks and we still see whites. Picture C then is set at 90 decibels. This is a very high dynamic range. There are many more grays being displayed, and now we're starting to lose some of our contrast. So this is considered a low contrast image. So each component of the ultrasound system has a different dynamic range. Dynamic range of information decreases the more that it is processed. So as I had mentioned earlier, the transducer has the greatest or the widest dynamic range of all system components. That means it's very sensitive to weak echoes and very sensitive to strong echoes. As we move through the ultrasound system, that sound goes into the receiver, which is going to have a lower or decreased dynamic range, and then off to the memory, which is going to even have a further decreased dynamic range, getting into the display and PAC system, which are even going to decrease more. So we find that the display and the archive system does have the smallest or narrowest dynamic range. This chart exemplifies a little bit what I had just said, with the transducer having a dynamic range of 120 decibels, down to the archive system, which only has a 10 to 30 decibel dynamic range. So when we look at the transducer at its 120 decibel range, that range is saying that the strongest echo that can be detected is 1 trillion times stronger than the weakest echo. When we get down to the archive system, though, with that 10 to 30 decibel range, we're saying that it is 10 to 100 times stronger than the weakest echo that can be displayed. So that's a really big difference in how sensitive each component is. We can kind of see this in action when you guys are working on your assignments for class. So think about when you're scanning live on the machine, everything looks beautiful. You're having the best dynamic range with what you see on the display, and there's minimum compression going on at this point. And then you're going to save those images onto a disk, and you hope that everything looks good. Well, at that point, everything has been compressed. The dynamic range is reduced because we've moved away from the ultrasound system. And then when you get home, you're going to open up your computer and you're going to put this information into a PowerPoint, you open it up and you're like, oh my gosh, I can't believe I actually took that picture. It's starting to look kind of junky. Well, that's because those pictures are still being compressed. Every time you save it, move it, change it to a different format, it gets a little bit more compressed. And so then when you make an open lab assignment in PowerPoint and then reopen it and it looks even worse, again, compression has happened. So our absolute purest, cleanest picture would be if we could go and look right at what the transducer is seeing. That doesn't happen though. So as all that information moves through the machine, compression occurs so we can keep accurate information, but stay within the dynamic range of each component. When I was describing the chart, I talked about how the transducer was 1,000,000,000 times stronger than the weakest signal, or could detect 1,000,000,000 times stronger, where our archive system was only able to detect signals 10 times as strong as the weakest, or up to 100 times as strong as the weakest. So it's just going back to how decibels work, in that it is a log 10 type number. So 40 decibels of dynamic range really means 10 times 10 times 10 times 10, which is 10,000. So if we had an ultrasound component that had a dynamic range of 40 decibels, then the strongest signal that it could detect would be 10,000 times stronger than the weakest signal. This should all be reviewed from learning about decibels last semester. So just recognize that the higher the decibel or dynamic range, the stronger or more sensitive it is to those stronger signals compared to weaker signals. The part of dynamic range that really affects our pictures, though, is how we end up seeing those pictures on our displays. It is either low contrast or high contrast. So dynamic range and compression, we kind of talk about those being used as to describe the number of choices or the number of grays that can be displayed. So with high or wide dynamic range, it means that we have lots of choices, but then that means low contrast imaging. Where if we have low or narrow dynamic range, that means there's few choices, but high contrast imaging. This is going to be more black and white. So here we can see what I was just talking about. On the left side, we have more choices. We still have bright whites and we still have dark blacks, but there's a lot more grays. This is considered a high dynamic range. This is going to be lower contrast. On the right, though, we have less choices. We still have bright whites, dark blacks, but there's less grays being used to display that information. That would be a low dynamic range and a high contrast picture. The problem with dynamic range, though, is that as we move through the system, one component following the next component typically has a narrower dynamic range than the one before it. So for example, if the receiver dynamic range is 100 decibels, and then the scan converter's dynamic range is only 60 decibels, we have to figure out how to get that information accurately compressed so the scan converter can use it without introducing any errors. If we don't use compression, then errors can occur, causing a distortion of our information. So compression is a technique that reduces dynamic range of the signal without introducing those errors. As a sonographer, you can adjust this compression. And when we think of compression, we have to think of 3 requirements of compression. The first one being that the largest signal remains the largest. Secondly, smallest signals still remain the smallest. And third, that the range of the signals is reduced. So here's an example of compression. When you guys are in class and you are getting your grades throughout the semester, oftentimes you are getting some sort of percentage out of 100. So we have our choices are from 0 to 100. That's 101 choices. At the end of the year, though, I assign you a grade on our scale of F to A. In conventional grading, that gives us 12 choices. When I put your grades in, the students with the highest percent still get the highest grade. The students with the lowest percent still get the lowest grade. So I now have less choices than I did from that 0 to 100% scale, but I haven't distorted the way that the students are ranked. If I wanted to compress that even further, I could go down to an A, B, C, D, or F grading scale, which reduces us to 5 choices. Again, the students with the highest percentages still get ranked with A's. The students with the lowest percentages still get ranked with F's. There's no distortion of how students are ranked. They are just categorized into less choices. So another kind of abstract way to think about this is if I gave you a bunch of crayons and said, using all the crayons, draw a tree, house, and a sky. So using this, you could put a lot of detail into your picture. You got a lot of choices going on, and you can draw a very nice image. However, if I start to compress your choices or take away crayons and tell you to draw with now 7 crayons that we have left, you can still actually draw a very detailed picture. We can still see the sky, clouds, we can tell the difference between everything. But now we are starting to get into a little bit more of a high contrast image. As we keep reducing our choices, we've now reduced down to 4. We can still see what everything is, but we just don't have as many choices. Continuing to bring choices down, even 3 crayons, we can tell it's a house, it's trees, it's sky, but we have compressed our choices without introducing errors. And then getting down to even 2 choices, we can still see it's a house, tree, and sky. We have compressed our choices down, but we have maintained the detail that we need. All right, so that's really pretty much it on dynamic range and compression. Again, it is a knob on your machine that you can adjust to get more black and white imaging. Make sure that you get a chance to try that out on your machine. I believe it is part of your physics book. If not, it is a very helpful tool to crispen up borders and make things that should be blacker, kind of getting rid of those low-level echoes because now they're assigned a black shade. So check that out on your machine and we'll get ready to test yourself. So number 1, what ultrasound component has the widest dynamic range? Is it A, transducer, B, receiver, C, memory, or D, display? Number 2, which image below is considered low contrast? Is it A, B, or C? And number 3, what unit is dynamic range measured in? A, decibels, B, centimeters, C, hertz, or D, frames per second?